In the heart of a processing plant in California's Central Valley, a river of tomatoes flows faster than the eye can track. They don't bounce. They don't bruise. They move as if guided by invisible hands, directed, protected, synchronized. Each one has a fragile skin, barely 2 millimeters thick. Each one can rupture with as little as 2.2 pounds per square inch. And yet, this system processes over 30 million tomatoes every day without reducing them to pulp. The secret isn't brute force or blind speed. It's engineering, precision engineering designed to handle fragility at an industrial scale. At the core of this operation is a machine that defies conventional mechanics. It moves soft biological units at a speed normally reserved for gravel or grain. But tomatoes aren't gravel. They're alive. They bruise. They burst. They rot. To move them efficiently, the machinery borrows principles from seed planters, where each seed must be dropped with surgical accuracy. In this case, the conveyor belts are lined with vibration-dampening materials, calibrated to absorb the exact shock threshold that would otherwise rupture the tomato's surface tension. It's not just transport, it's force distribution under continuous flow. To understand what's happening here, imagine the conveyor systems used in open-pit coal mining. There, tons of material move non-stop over kilometers of belts, regulated by flow sensors and motorized speed gates. The tomato line uses a similar principle, but on a softer, far more sensitive scale. Instead of steel chutes, it relies on suspended sorting trays and dynamic rollers with micro-delay algorithms. Each part of the system adjusts in real time, not for weight, but for texture. The tomatoes aren't crushed under volume. They're carried as if cushioned by air. This is where agriculture meets biomechanics. A ripe tomato has an internal pressure threshold of just 1.5 to 2.2 psi. That's less than the pressure you apply when holding a light bulb between your fingers. The entire sorting system is therefore built around avoiding micro-impacts. Shocks you wouldn't feel, but that can destroy a tomato's cellular integrity. To prevent this, multi-stage velocity controls and deceleration ramps reduce kinetic transfer. The belts aren't just fast. They're smart. They know when to slow down, when to transfer, when to pause. To grasp the magnitude of this process, consider this. At full capacity, a single sorting line can handle up to 1,500 tomatoes per second. Multiply that by the number of lines in a regional facility, and you reach a scale of 130 million fruits per day. Each one sorted, each one scanned, each one weighed, inspected, and directed with near-perfect precision. There's no room for randomness. Every movement is accounted for, every surface calibrated, every trajectory calculated. Overlay this system onto the blueprint of a bulk coal loader, and you'll start to see the brilliance. Both operations move high volumes with flow modulation at the core. But while coal tolerates rough transitions, tomatoes demand balance. The structural challenge is the same, continuous movement of mass. But the execution requires softness engineered into every component. It's not just logistics. It's a choreography of velocity, pressure, and time. And this is only the beginning. Because before the tomato ever reaches a supermarket shelf, it must survive sorting, packaging, transport, and climate. Each step as critical as the last. But the first move, the first decision, the first vibration, that all begins here, on a belt, in a facility, inside a machine designed not for dominance, but for sensitivity. A machine that redefined what it means to move a fruit, quietly, powerfully, every second. On the surface, a tomato looks perfect, round, firm, and ripe. But inside, it might already be broken. That's the paradox of impact damage in fresh produce logistics. The rupture doesn't always show up as a visible crack. Often it's molecular. A micro-shock during sorting, barely a tremor to the machinery, can begin a chain reaction that softens the flesh, activates enzymes, and sets a 48-hour countdown to decay. Once that clock starts, the tomato won't survive the journey to the shelf. And yet, thousands of these invisible breakdowns happen before the crate even leaves the facility. This is where traditional sorting lines fall short. Designed for volume, not sensitivity, they treat all cargo the same. But tomatoes aren't apples. Their skin isn't just a barrier, it's a pressure membrane. Standard polymer trays and angled deflectors, built for speed, bounce the fruit from point to point. That movement accumulates energy, and energy turns into stress. So even if the tomato looks unharmed, it has already absorbed damage that shortens its market life. And when this loss repeats across tens of thousands of units daily, the cost becomes structural. To change that reality, engineers turned to a field that couldn't be more different: minimally invasive surgery. From there came the idea of robotic grippers with pressure feedback loops. These systems don't just grab, they measure, adapt, and respond. They adjust their grip strength in real time, sensing the resistance of each individual fruit. Combined with air cushion conveyors, they enable zero-contact transfers between belts, maintaining movement without impact. These technologies, initially built to handle arteries and nerves, are now used to move produce with the same level of care. The results are measurable. At the University of California, Davis, researchers found that tomatoes kept in low-pressure, vibration-free zones for just 10 minutes. Post-sorting had a 29% longer shelf life. That's not marketing. That's biochemical reality. By reducing mechanical stress before packaging, the fruit retains its structural integrity and ripens in a stable, gradual curve, essential for long-haul logistics. It's a 10-minute window that can change the value of an entire harvest. One tomato processor in Brazil decided to test this approach. They replaced hard, reusable plastic trays with biodegradable soft-shell bins, each lined with impact-dampening ridges molded from agricultural waste fibers. The change reduced their post-sort rejection rate by over 12% in a single season. Less waste, more product, better transport performance. But the success wasn't in the bin. It was in understanding that logistics begins with material design, not just trucks and routes. This forces a deeper question. If your tomatoes are moving faster than your visual quality controls can follow, what else are you missing? When a system is calibrated for speed, but not for biological sensitivity, it becomes a mechanism of waste disguised as efficiency. Every skipped frame, every missed bruise, every undetected fault becomes a future loss. Quiet, cumulative, and costly. And this is just the first threshold. Because once the fruit is sorted and intact, it still has to survive temperature. And in tomato logistics, the cold can be just as lethal as the shock. Temperature can preserve, but in the case of tomatoes, it can also destroy. Beneath the bright surface of refrigerated logistics lies a biological contradiction. When exposed to cold, tomatoes begin to lose the very qualities that make them marketable. Below 12 degrees Celsius, the fruit's internal enzymes, especially those responsible for ripening and flavor development, shut down. The texture becomes mealy. The skin may stay intact, but the flesh turns soft, dull, and lifeless. It arrives looking perfect, but feeling wrong. In the world of export-grade produce, that gap between appearance and texture is enough to collapse a sale. The problem is systemic. Most cold chains are designed for endurance, standardized to extend shelf life by slowing down biological activity. But tomatoes aren't inert cargo. They continue to live, breathe, and ripen after harvest. Interrupt that rhythm too early, and you get a product that survives the trip but loses its purpose. For decades, this led to a trade-off: speed over quality, cold over character. But new technologies are redefining what preservation means. By stabilizing temperature without sabotaging physiology, one of the most compelling innovations comes from a surprisingly simple source: fermentation gases. Certain transit bins now incorporate modular insulation systems that use the tomato's own ethylene emissions, combined with heat generated during fermentation of nearby plant matter, to regulate internal temperature. These containers aren't powered by compressors or external chillers. They adapt, using airflow channels and thermal buffering materials to keep temperatures just above the damage threshold. It's a method inspired by adaptive composting, but applied to post-harvest logistics. The results have been dramatic. In controlled exports from Spain to Northern Europe, tomatoes transported in ambient adaptive containers maintained consumer-grade firmness 36% longer than those moved under traditional refrigeration. That extra time means broader distribution, fewer rejections, and less pressure on pricing. And because these systems operate without electrical inputs, they also reduce energy costs, solving an economic and environmental problem at the same time. Other countries are already adapting. In southern Italy, one short-haul pilot project redesigned its crate interiors to prevent direct contact with metallic surfaces. The solution was straightforward: a floating frame system using biodegradable polymers to suspend the tomatoes a few millimeters above the hard floor of the container. The result? A 22% increase in viable deliveries, especially during nighttime transits when dew and surface cold can amplify chilling effects. None of these innovations come from guessing. They come from rethinking logistics, not as a question of route, but as a question of contact and reaction. In delicate crops like tomatoes, every minute of chilling saved in transit can translate into hours of lost shelf life at the endpoint. And that leads to one final, unavoidable question. What is the point of arriving early if the product arrives already texturally dead? This is the dilemma at the core of tomato transport. Not how far it moves, not how fast it travels, but how much it can endure. And increasingly, the answer is not in the kilometer, but in the gram. Not in the clock, but in the cell. What matters now is sensitivity. And the machines that survive the future of food logistics will be those that understand softness as well as strength. We often think of logistics in terms of distance. Tons moved, hours saved, kilometers covered. But when it comes to tomatoes, these metrics tell only part of the story. The real breakthroughs happen not in how far the fruit travels, but in how gently it's handled. Because this isn't the movement of cargo. It's the orchestration of living, delicate units, each one shaped by time, pressure, and temperature. The future of tomato transport won't be measured in volume per hour. It will be measured in grams of force, in degrees of tolerance, in how little damage is done by how much movement. In agricultural mechanics, there's a term that rarely reaches public discussion: inertial sensitivity. It describes how a physical object responds to acceleration, shock, and directional change. For grains or roots, the threshold is high. For tomatoes, it's microscopic. That means every stop, every curve, every transfer must be calculated to avoid internal collapse. In traditional logistics, those tolerances are irrelevant. In tomato transport, they are everything. A system that treats fruit like freight will lose both time and product. But a system that treats fruit like soft biological material, alive, unstable, and valuable, will win the future. Some companies are already making this transition. A Dutch exporter specializing in bell peppers developed smart intermodal crates that monitor the internal load during transit. These containers are equipped with suspension elements that adjust in real time based on the weight shift of the produce inside. If a shipment encounters rough roads or sudden deceleration, the crate's base softens its tension to absorb the force. What started as a stability mechanism has become a model for fresh produce transport across Europe, replacing fixed, rigid systems with ones that adapt dynamically to fragility. The key is to stop thinking of fruit as a bulk commodity. A tomato isn't just mass. It's memory. It carries within it the record of every bump, every drop, every change in temperature. Logistics, in this context, becomes less about movement and more about custody. How gently was it carried? How evenly was it cooled? How precisely was it transitioned from machine to crate to truck? These are not romantic questions. They are operational questions, and they decide whether the tomato ends up on the shelf or in the discard bin. That's why the true revolution in agribusiness won't come only from faster machines or cheaper freight. It will come from systems that listen to the fruit, from belts that adjust pressure based on texture feedback, from crates that modulate tension with each jolt of the trailer. From cold chains that think in thresholds, not just thermostats. This isn't softness, it's intelligence. Mechanical, digital, agricultural intelligence applied to a problem as old as farming: how to preserve life through movement. Because in the end, precision isn't just in the machine, it's in the philosophy behind the machine. In tomato logistics, the future doesn't belong to those who move the most. It belongs to those who move without harming, without wasting, without rushing past what matters. And sometimes that means trading kilometers per hour for something far more powerful: control per second. That's how 30 million tomatoes can move each day without ever losing their value, their texture, or their purpose. Quietly, repeatedly, reliably, as if each one mattered. Because in this system, it does. Comment 1 if you'd like to see the inside of one of these tomato factories. What surprised you most? Air cushions, the cold trap, or how many tomatoes move per second?